Welcome to SciFlux. Today's video is all about what's new in engineering, the innovations and designs redefining how we build the future. If you like our content, please don't forget to subscribe to the channel and join our newsletter to keep up with the newest discoveries shaping our world. Let's start. From home lighting to large renewable grids, our energy systems rely on precise control. Model predictive control has been the gold standard, but it's slow and computationally heavy, limiting its use in fast or compact hardware. A new solution is emerging: differentiable predictive control, or DPC. Instead of solving complex calculations in real time, DPC trains a neural network offline to learn the optimal control strategy. The result is a lightweight, high-speed controller built for embedded systems. Tests show DPC tracks targets accurately, adapts to changing conditions, and slashes computational demands compared to traditional MPC. This opens the door to smarter, faster control for electric vehicles, renewable grids, and industrial power systems. DPC has the potential to redefine power management, making advanced, precise control more efficient and widely accessible. Next work. This breakthrough strengthens the foundation of modern power systems, making them more resilient and ready for a more connected world. Every electronic device, from your phone to cloud servers, depends on stable, reliable power. DC-DC buck converters play a central role by stepping down voltage efficiently. But sudden surges or harsh conditions can damage these circuits, so precise current-limiting protection is essential. Many existing protection schemes struggle with delays and limited bandwidth. To solve this, researchers developed a high-precision current-limiting design that uses a simplified sampling method and a fast turn-off strategy. The result is accurate current control with low power loss and a compact circuit. Tests delivered strong results: 95.6% peak efficiency and a remarkably stable current limit, drifting only 4.35% across temperatures from -40 degrees Celsius to 125 degrees Celsius. This level of reliability protects electronics in demanding settings, from automotive and industrial systems to critical medical devices. Next paper. Billions of people fly every year, connecting the world but producing major carbon emissions. Electric and hydrogen aircraft are promising, but not ready for widespread use yet. That's why sustainable aviation fuels, or SAF, matter now. SAF works with today's engines and infrastructure, offering an immediate emissions-cutting solution. Researchers tested several blends, analyzing chemistry, combustion, and engine performance. The results? Up to 80% lower lifecycle carbon emissions, with the same thrust, stability, and reliability as conventional jet fuel. SAF gives airlines a ready, high-performance way to shrink their carbon footprint today, paving the way for cleaner skies long before new aircraft technologies arrive. Moving forward, electric vehicles deliver clean, powerful performance, but their batteries, motors, and power electronics need continuous, accurate monitoring. The problem is that EVs operate in constantly changing conditions: urban stops, highway speeds, heat, cold. Traditional diagnostic AI, trained on stable data, often fails when the environment shifts. Deep Transfer Learning, or DTL, solves this. It combines deep learning's pattern recognition strength with transfer learning's adaptability, creating diagnostic models that stay accurate even as conditions change. Applied to EV batteries, motors, and power electronics, DTL delivers reliable fault detection across diverse operating scenarios. The result? Safer EVs, longer component life, smarter maintenance, and more consistent performance. Deep Transfer Learning is turning electric vehicles into more resilient, real-world ready systems. Seaports power global trade, and in Egypt, the port of Damietta handles 90% of the country's goods. But high energy use, emissions, and complex logistics demanded a transformation. Damietta modernized with a multi-purpose berth to increase capacity, a just-in-time system to streamline cargo flow, solar power and cleaner vehicles to cut emissions, and a digital port single window to simplify processes. The port also added green areas and solar lighting to improve its environmental footprint. The impact is clear: higher energy efficiency, lower emissions, smoother operations, and greater transparency. Damietta now stands as a smart, sustainable port, proof that technology and environmental responsibility can move in sync. Its success offers a blueprint for ports worldwide, showing that efficiency and sustainability can scale together. This paper, it's a smart reminder that powerful innovations often start by rethinking the tools we already have. Our world runs on electricity, and DC microgrids are becoming essential for homes, businesses, and critical infrastructure. But these systems often suffer from voltage imbalances that strain equipment and reduce efficiency. Researchers introduced a new approach called dual power transmission multiplexing, or DPTM. It transforms idle permanent magnet motors into active microgrid stabilizers, balancing voltage while simultaneously storing energy. Intelligent control algorithms let the system adapt in real time, shifting between functions automatically. Tests confirm that DPTM boosts stability and efficiency without adding complex hardware. By reusing existing motors, it simplifies microgrid control, protects equipment, and accelerates the transition to cleaner, more reliable local power. Imagine global trade running on guesswork. Every ship's arrival shaped by unpredictable wind and waves, causing delays, wasted fuel, and safety risks. Researchers developed a data-driven framework combining weather forecasts with ship performance simulations. By modeling how waves and wind affect speed and how forecast errors translate into uncertainty, they provide a realistic range of possible ship speeds. Instead of a single estimate, captains and planners get actionable insights to optimize routes, schedules, and fuel use. This innovation brings unprecedented precision to maritime logistics, keeping global trade moving smoothly even across unpredictable oceans. Now, imagine a home fully powered by sunlight, with batteries storing energy for cloudy days. Simple in theory, but managing solar panels, batteries, and appliances efficiently is tricky. Researchers created a dual DC port dual output converter that delivers power from both panels and batteries in a single step to multiple AC loads. Its smart control system, called Virtual Space Vector Pulse Width Modulation, precisely manages energy flow, keeping the system efficient and easy to use. Tests show it maximizes efficiency, reduces waste, and cuts costs, making solar battery homes practical and accessible. This innovation brings us closer to a smarter, cleaner, and more sustainable energy future. Picture a future powered by fusion reactors, particle accelerators, and advanced medical imaging. Technologies that rely on high-temperature superconductors, carrying massive currents without resistance, but only at extreme cold. The challenge is delivering high currents efficiently at cryogenic temperatures. Traditional power converters waste energy and generate heat, making cooling harder. Researchers developed a 3-switch T-type bridge using gallium nitride transistors. Only one transistor conducts at a time, slashing resistance, heat, and energy loss. Tests at liquid nitrogen temperatures showed 50% lower conduction losses than standard designs. This breakthrough enables smaller cooling systems, lower costs, and more efficient superconducting magnets, bringing fusion, accelerators, and other high-power technologies closer to reality. By optimizing power under extreme conditions, superconductors can truly power the future. Picture the power systems driving our world: EV fast chargers, renewable grids, and battery converters. They move energy efficiently, but bidirectional CLLLC resonant converters often struggle to step down voltage, especially above their resonant frequency. Researchers developed a hybrid bridge arm control strategy, letting the converter switch dynamically between half-bridge, full-bridge, and full half-bridge modes without extra components, all at a fixed switching frequency. The result? Smoother operation, higher efficiency, and flexible voltage control. Tests on a 10-kilowatt prototype confirmed real-world performance. For EV charging, this means faster, more adaptable stations. For renewable energy, it ensures smoother integration of solar and wind power. By rethinking the converter's design, this innovation makes power electronics smarter, more reliable, and ready for the energy demands of the future. Last paper for today talks about a disease that steals memories, slows movement, or distorts reality. Alzheimer's, Parkinson's, ALS. Treating these disorders is tough because the blood-brain barrier blocks most drugs from reaching the brain. Now, exosomes offer a breakthrough. These tiny natural delivery packages can cross the barrier, carrying proteins, genes, or drugs directly to targeted neurons. Scientists are engineering them to deliver therapies precisely, repair damaged brain circuits, and reduce side effects. The potential is enormous: accurate drug delivery and treatments that actively support brain healing. While challenges like scaling production remain, exosomes could finally make effective therapies for neurodegenerative diseases a reality. That's it for today's video about the engineering breakthroughs. Don't forget to subscribe to SciFlux and join our newsletter to keep up with the newest discoveries. See you tomorrow!